In this video, we'll be doing a review for Exam 3. We'll be going over a list of topics that we've covered since the previous exams, and I'm also going to include another look at functions. There's a lot that goes into functions, so I have the list on the side of the screen. They're identified by their prototypes or their function signature, which identifies the return type of the function, the name of the function, and what kind of parameters or pieces of information are taken in by the function. These, along with the pre and post conditions, describe what the function is going to do. So remember, your pre and post conditions are comments that describe the purpose of the function. And if we have both of these, then we know exactly what a function is going to do. So therefore, when we write a function, we also need to provide this information. The prototype goes with the pre-processor directives. That goes at the top of the program after the included libraries and the defined constants, but before the main function. The pre and post conditions should go with the function, and the function bodies themselves are located after main. Well, the great thing about functions is they introduce modularity to our code and also reusability. Once we've written a function, we don't typically need to write it again. We can just reuse it. This is really great for common tasks like comparisons or swaps. What we need to pay attention to is our parameter list, our actual parameters versus our formal parameters. Formal parameters are in the function definition. They're the ones in the parameter list in the function prototype or function signature. The actual parameters are the variables or expressions that are used when we actually call a function. These are two kind of separate ideas. The formal parameters, or the one in the parameter list or in the function definition, become the local variables to that function. It's okay for formal and actual parameters to have the same name, but it's also okay if they're different, because the actual parameters are the ones that are being passed to the function. And what matters for actual parameters is that they're compatible with the type of the formal parameter. This is true for both pass by value and pass by reference functions. In a pass by value function, only the value is passed from function to function. So if we're passing, say, an integer sum to a function, we're only passing a copy of what sum contains. But if we pass by reference, we're going to pass the location of the variable. This allows us to change things at the memory level, and it allows our functions to make changes to things that it wouldn't otherwise have access to. For example, with our returns, we're only ever able to return one value. So if we have a function that needs to modify more than one value, like a swap, for example, we have to have pointers so that we can modify things at the memory level instead of just via the return. So let's look at some example questions. This first question says, which of the following correctly passes the reference to the variable int max to the function f? So we're not given any information about f. We're just told that it takes in a reference to an integer, and it's called f. We're also told that max is declared as an integer and not an integer pointer. So for f to take in a reference, it needs to take in something that is compatible. So things that are compatible with pointers are other integer pointers or addresses to where integers are located. So for us to pass a reference to int max, we need to pass in the address of max to function f. Here's a second question. It says, what is the purpose of the function below? And that n is the length of a. So we're not given the function signature or the pre and post conditions. We kind of have to infer what f is doing just by tracing through it. So at the very top of the function body, we can see int a and then square brackets. So that tells us that a is an array. But it doesn't tell us the size. So that's what n is for. It says n is the length of a. A is an array, and n is the size of that array. Now f also returns an integer. So we need to figure out what integer is f returning and why might it be doing that. So inside this function we have an integer I and an integer m that gets the first value in the array. So when we're tracing things like this, I think it's really helpful to have an example. So we're just going to make one up. Let's have a relatively small array that has these 5 values in it. This would be declared integer array, and then we can define its initial values inside these curly brackets. So it'll have 4, 3, 1, 5, and 2 in it, and in that order. And then in our function, we have I, which hasn't been given in a value yet, and m, which gets a at 0. Our other parameter is n, and n will be 5 since that's the length of the array. In this first element, a sub 0 is 4. So this is where we're starting off in just the first line of our function over here. I has been declared but doesn't have a value. M has been declared and gets the value that's in the first spot of the array, which is 4. Here's our sample array, and n will be 5. Okay, so following that, we're going to set I equal to 1. And as long as I is less than n, we'll go into this loop and check to see if m is less than a at I. So we want to know if m, which is currently 4, is less than a at index 1. Since it's not, 4 is not less than 3, we're not going to do anything, and instead we're going to increment I. Now that I is 2, we'll check to see if m is less than what's in the array at index 2, and 4 is not less than 1, so we're just going to increment I. And now we'll check to see if m, still 4, is less than a at index 3. 0, 1, 2, 3. 4 is less than 5, so we're going to set m equal to that value. We're going to set m equal to a at index 3. We'll set m equal to 5 and increment I. And then we'll check to see if m is less than a at index 4. 5 is not less than 2, so we're not going to modify m again. We will increment I to break out of the loop because 5 is not less than 5, and then we're going to return m. So we're going to be returning 5, and we want to know, what does that mean? Well, 5 is the biggest value in the array, and every time we examine an element in the array, we're checking to see if it's bigger than the value that we're storing. And if it is, we update that value. So our goal is to traverse the array and find the biggest one. And since we return that value, the purpose of this function is to return the maximal value of a. This next question asks us to create our own function. This is to simulate the power function without including the math library. So we can't make any actual calls to the power function, we have to do it ourselves. We can make it very similar to the power function, so we can have a very similar function signature, and the task it's going to complete will be the same. So this is a very similar beginning to the power function. All I've changed is the name. It's going to return a double and take in two double parameters, x and y. And it's going to return x raised to the power of y, or x raised y. So let's think about what we're trying to accomplish. Let's suppose x is equal to 2 and y is equal to 3. We want to return 2 raised 3, or 2 times itself 3 times. This is the action we need to complete since we don't have any power operators. We have to recreate this action ourselves. So we want to take x and multiply it by itself y times. So we want a loop that will start at 0 and go to y, where we can take results and multiply it by x for each iteration. So the real key to this process is starting results at 1. So if we started at 0 and then we multiply anything by it, we're going to get 0 back. But if we multiply x by 1 in our first iteration, then we'll get x. And then we'll continue to multiply in x until we get to y. And when we're done, we need to return our results. And this is a pass-by-value function. Neither x nor y are pointers or arrays or references of any kind. If we tried to make any changes to x and y in the function, those changes would not be evident outside the locality of this function that we've created, myPow. So we have to return our results, and result has to match the data type of our return type. And that way the parent function can receive the value that is x raised y. So let's look at a different example that does require some pointer usage. It says create a function to calculate if a number is a perfect square. We're given the function signature, in this case, the function prototype. It says this will be a void function. It takes in 3 parameters, n, which is going to be the number we're evaluating, perfect pointer, which will be a flag. It says if the integer n is not a perfect square, then this guy should be equal to 0 and 1 otherwise. This root pointer will be the root of n if it's a perfect square, or it'll be the root of the next perfect square if n is not a perfect square. Because we're trying to modify 2 different values, we have to use pointers. We want to modify this pointer and this pointer, so we can't do that with a single return value. We need to be able to modify these guys at the memory level. First, we need to find out if n is a perfect square. So perfect squares are those numbers that have integers as their square roots, like 4, 9, 16, 25, etc. So this one is 2 times 2, this one's 3 times 3, this is 4 times 4, this is 5 times 5. So similarly, we're going to find out if n is equal to the same integer times itself, so the same integer squared, or I times I. And we're going to start I at 1 and check to see if n is 1 times 1, 2 times 2, 3 times 3, 4 times 4, but we need to stop checking once we get higher than n. So in this loop, we're going to start I at 1 and increment I until we find an I squared that is greater than or equal to n. And that's when we'll stop. Then we can check to see if the I that we've arrived at, if I squared is strictly equal to n. If it is, then n is a perfect square. So if I times I is equal to n, it's a perfect square, and we need to go to where perfect pointer is pointing and set that equal to 1. And if not, then we need to go to where perfect pointer is pointing and set it equal to 0 instead. And the last thing we need to do is set root pointer. So we're going to go to where root pointer is pointer and set it equal to I, which is the root of the nearest perfect square. And we want to return at the end. So we're going to do I times I until we get to n, and if that's exactly n, then I times I is equal to n, and n is a perfect square, and I is its root. Otherwise, I is still the root of the nearest perfect square. Our final example question for functions is a tracing question with pointers that says, what is the output of the following program? Well, this program contains one function that takes in 2 integer pointers. So we're going to be tracing pointers. In main, and we'll keep track of our scopes or our localities over here. Those are the variables belonging to the 2 different functions we have. In main, we have variable declaration for A, which starts at 6, B, which starts at 7, and C, which starts at 8. Function F will have its own locality, and we also want to track the output, because it says what is the output of this program. Now B is going to be assigned the value that is returned from F, where F is given the parameters, the address of C as its first parameter, and the address of A as its second parameter. F's local variables are pointers A and B. So its first parameter, this integer pointer A, is going to receive the address of C from main. So we would say that A inside function F points at C in main. And the second parameter, pointer B in F, receives the address of A from main from this function call. First parameter gets the address of C, second parameter gets the address of A. So we would say that B in F points at A in main, and we transfer control to F. So we're going to come down here. And our first line in F says, go to where A is pointing, and assign it the value of what A is pointing at, plus the value of what B is pointing at. So A is pointing at C. A is pointing at C in main. and C is currently holding the value A. B is pointing at A in main, which is currently holding the value 6. So if we add those two together, we will get 14. And we want to go to where A is pointing and put 14 there. Go to where A is pointing and put 14. Then go to where B is pointing and assign it the value of what A is pointing at minus what B is pointing at. Well, A is still pointing at C, which now has the value 14. B is pointing at A, which has the value 6. So we're going to take 14 and subtract 6, which will give us 8. We're going to go to where B is pointing and put 8 there. B is pointing at A, so we're going to go to A in main and put 8 there. Then we're going to print what A is pointing at and what B is pointing at. So this will be our first case of output. A is pointing at C, which has 14. B is pointing at A, which has 8. And we're going to return 3 times what B is pointing at. So B is pointing at A, which is 8, and 3 times 8 is 24. And that gets returned to B in main. So B will become 24. Then we're going to print the values of A, B, and C as they exist in main. This is our second case of output. We're going to print A, B, and C. So we'll print 8, 24, and 14. And for this type of question, we want to copy those values into these boxes. The first case of output, A is 14, B is 8. And the second one, A is 8, B is 24, and C is 14. Now we can move on to strings. Strings are a really interesting part of the C programming language. They're a special form of character array. And it's what we call null character terminated. They're created very similar to any other array. They have the data type character, whatever name we would like to give that collection of characters, and then a size. The primary difference between arrays that are strings and other arrays is that we have to reserve one of these spaces for the null character. We can print them to the screen and read them from files in the keyboard using the string percent code %s. Let's say, for an example, that our word is soda. It'll be comprised of the characters S, O, D, and A, but it has to end with the null character in order to be considered a string. Now we can make character arrays that are not strings, but in order for it to be considered a string, it has to have this null character at the end. And when we're using the percent code for it, %s, and say a printf function call, the compiler knows to print all of the characters up to the null character. And similar when we're reading it in. If we read in something using %s, it wants to read all of the characters and then add a null character to the end. And the functions that we learned in the string library also rely on what we call this null character termination. So in order for a character array to be considered a string, it has to have the null character at the end. Let's do a brief recap of these 4 functions that we focused on. The first is string copy, which copies the second parameter into the first parameter. It sets the contents of S2 into S1. Because they're strings, we can't use our standard assignment operator, but we can use string copy to accomplish the same effect. what we'll do is we'll copy all of the individual characters of S2 into S1, including the null character at the end. Next one is string length. And what string length does is it counts all of the characters up to the null character. So in our example up here, it would count all of the characters in our string, but not the null character. So it would give us a string length of 4, because there are 4 characters before the null character. Our third one is string compare. Since strings are special forms of character arrays, we can't use any of our standard relational operators. We wouldn't be able to use less than or greater than and expect them to return a value that would be meaningful to us. Instead, we use the string compare function. And what this returns is a negative value if S1 comes before S2. And the technical term is lexicographically, which means that it's based on the ASCII value of the characters. If S1 and S2 have this same casing for every character, then it's just an alphabetical comparison. This will return a positive value if S2 comes before S1, and it will return exactly 0 if both strings are the same. Our final one is called string concatenation, which also takes in 2 strings, S1 and S2. And what it does is it's going to append S2 onto the end of S1. So S1 will still have itself at the beginning of the string, and then we'll have on the end of it S2 as well. So let's look at some example questions for strings. This one says, the function below is most like which function in the string library? We've specifically talked about these 4 functions. Now there are several more in the string library, but this will only be based on the ones that we've actually covered. So it's going to match up with one of the 4 that we've talked about, and we just need to figure out which one. So just from the 4 that we're familiar with, string copy, string length, string compare, or string concatenate, which one does this most closely resemble? Well, we can start with the prototype, or the function signature. This one takes in 2 character arrays, which we assume are strings, and returns an integer. So which of our functions takes in 2 strings and returns an integer? Well, string copy and string concatenate both take in 2 strings, but they don't return anything. String length returns an integer, but only takes in 1 string. So that leaves us with string compare, the one that takes in 2 strings and returns an integer. So we expect the rest of this function to resemble string compare, and we're going to trace through it to make sure. We start with a counter I at 0, and we're going to run a loop that continues as long as the character in the ith location of both strings is not the null character. So we're going to start at the beginning and continue until either string ends. And we're going to compare characters in the same location, and if they're different, we're going to return a value. If A comes first, we're going to return a negative value. If B comes first, we're going to return a positive value. If we get to the end of one of the strings, we'll do another check in case one is a prefix of the other. If A is less than B, return a negative value. If B is less than A, return a positive value. Otherwise, return 0. Well, this is exactly how string compare behaves. We compare characters in the same location of two strings until we find a difference. And as soon as we find a difference, we'll return a negative or a positive based on those ASCII values. And if we never find a difference, we're going to return 0. So this is string compare. I also have a tracing question. So fill in the blank style question. We're going to type a string into this blank. So we have to be very cautious here because only exact answers will count. And there's a little warning that says the input field is case sensitive as well because uppercase values and lowercase values of characters have different ASCII values. We want to know what the output's going to be for this particular program that creates a character array and has an integer I that starts at 0 and copies into this character array using the string copy function the word computer in all capital letters. So we're going to copy that into Word, and then we're going to traverse this array until we get to the null character. So let's examine the array representation that's going on here. C will be in index 0, O will be in index 1, M will be in index 2, P will be in index 3, U will be in index 4, T will be in index 5, E will be in index 6, R will be in index 7, and in index 8, we'll have our null character. This is what makes it a string. And I starts at 0. It says as long as word at index I is not equal to the null character, run the body of this loop, check to see if I mod 2 is equal to 0. So 0 mod 2 is 0. So we're going to go into Word at index I, at index 0, and set it equal to Word at index I plus 1, which is 1. So I'm going to go to I at 0 and set it equal to the array at index 1. Copy just that single character over. And then I'm going to increment I. So we'll check to see if word at index I is equal to the null character. It's not. Well, and then we'll check to see if I mod 2 is equal to 0. And in this case, it's not. 1 mod 2 is equal to 1. So we'll just increment I and do our next iteration. Haven't reached the end of the string yet, so we'll check I mod 2. 2 mod 2 is 0. So we'll go into our array at index 2 and assign it the character that's in the array at index 3. And then increment I. We're not at the end of the string, so we're going to do 3 mod 2, which is 1, which is not 0, so we can increment I, check our next iteration. Not at the end of the string yet, so do 4 mod 2. 4 mod 2 is 0, so go into the array at index 4 and assign it the character at the array at index 5. And then increment I. Haven't yet reached the null character, and this number does not equal 0 when modded by 2. We're going to increment I. Still not quite at the null character yet, so check I mod 2. 6 mod 2 is 0, so go into the array at index 6 and assign it the value of the array at index 7. And increment I. Now, word at I is not equal to the null character yet, right? So we're going to increment I one more time. And we'll be checking now is word at index 8 equal to the null character? And since it is, that's what's going to break us out of this loop. And it says now print this word. When we're using the %s code, we're going to print everything up to the null character. So we're going to print these 8 characters with no spaces in between them, and using the correct casing because this field is case sensitive. Let's also do a coding question. This one says write a function that takes in 2 strings. The function should combine the 2 strings with the string that comes first lexicographically first. There should be a space between the 2 strings. Print the resultant string on one line and print the length of the resultant string on one line. Now we're not told to make any modifications to the strings that we're going to get, and we're not told to return anything. So we're going to make this a void function that I'm going to call string combine. It takes in 2 strings, S1 and S2, 2 character arrays. That's going to now combine them into a separate string. Okay. So I'm going to make a new string, the one that I want to print out, and its length needs to be big enough to hold both of our input strings. Since we're going to combine them, we need something that is big enough to hold both and the space that comes between it that we're supposed to add in, and the null character at the end. So it needs to be long enough to hold S1 and S2 and 2 additional spaces, one for the null character and one for the empty space. Now after that, we're able to make our comparison. We're going to use string compare on S1 and S2 to see which comes first. If this returns a negative value, then S1 comes first. And we want to put S1 into our print word first. Print word's currently empty, it's uninitialized, so we want to first put S1 in it, if S1 comes first lexicographically. And then we want to add to it, using string concatenate, a single space, and then add to that, using string concatenate, that second string. So we want to combine the 2 strings into a single string with a space between them. So combine the 2 strings with the string that comes first lexicographically first, with a space in between them. Now if S1 doesn't come first, we want to do this in the opposite order, where we want to put into print word S2 first, and then add onto it a space, and then S1. Once we've combined them, we want to print the resultant string on one line. So I'm going to print a string and then a new line. And this will kind of ensure that it's by itself. So we'll print the resultant string on one line. So print word. And then print the length of the string on a separate line. So this one will also get a new line character, but it's an integer. And we want the length of our new string that we created, the string length of print word. And when we're done, we can return from the function. Another cool thing that we can do with strings is make collections of them. Usually when we say collections, we mean an array. So an array of strings is an array of character arrays, which is just a 2-dimensional array. So if we were to make a two-dimensional array like this, we would say each row is a string that can be up to 19 characters long, because the size of each row is 20, and we need room for the null character. So each row would be a string that can be up to 19 characters long. In this particular declaration, there are 10 rows, so there can be 10 strings. So this particular declaration says there's 10 strings, and each string can be up to 19 characters long, with the null character at the end. The way two-dimensional arrays are organized in memory is that all of the rows are stored contiguously, which means we can use that to our advantage with strings. If we want to print out just one of these strings, then we could print out using %s code and just specify the row. Because what the compiler would do is go to row 0 and just print everything across the row until it gets to the null character. So for our sample question, it says, write a function that will count the number of times the word the appears in a collection of words. So we need to traverse a two-dimensional array where each row is a string. We need to compare it to the word the. And we should assume we're going to return an integer since we're looking for a count of the number of times the words the appears. I'll call this function count the. And it needs to take in a two-dimensional array of strings. And for our other parameter, we'll have the number of words. One of the odd things about the way arrays are organized in C is that when we pass them as a parameter, we have to specify the length of the row. We don't technically have to specify the number of rows, but we do have to specify the length. So I'm going to include the number of rows as our second parameter. And we need to traverse this array and count how many times the row is the same as the word the. So we're going to go through each row and check to see if the ith row is the same as the string literal the. So we need to make the into a string, so we're going to put it in double quotation marks. And if string compare gives us a 0, meaning they're the same, then we can increment count. And at the end of the function, we're going to return that count to tell the parent function how many times the word the appeared in that collection. And that will wrap up strings for us, which means we can move on to structures. Structures are a really cool element of C that allows us to relate different pieces of information that don't necessarily have the same type. We essentially get to create our own data types. These definitions go with our preprocessor directives, and they typically start with the keyword struct. We then give it a name, and then inside a set of curly brackets, we're going to identify the fields of the structure. In each field, each piece of related information we're trying to contain needs both a data type and a name. And we can relate as many pieces of information as we want. We can make integers, doubles, characters, floats, arrays, other structures, anything we want to relate, we can define as part of our structure as one of the fields that we're going to have just by putting it in this set of brackets. And we'll always end with our semicolon. We're going to be working with a specific example for several of our sample questions. But we're going to build a structure of soda bottles called case. So the name of our structure will be struct case, and it's going to contain a number of bottles in the case, which will be an integer. We're only going to store whole bottles there. We also want the type of soda, which will be a string. And all of the sodas in our case are defined to be of the same type. So you're going to relate these two different pieces of information. We're going to essentially package them together, the type of soda and the number of bottles that we have of it. This will be struct case. Once we've defined it, and remember this goes in our preprocessor directives, we can then create variables of that type. Before we get there, I have a question that says, which of the following is a valid struct definition? So which of these sort of matches the outline that we have here and contains valid syntax? So there's some that we can rule out right away. This one, labeled C, doesn't have any curly brackets, so we can rule it out right away. This first one up here has a variable that starts with an integer, which is not valid syntax. We can't write a variable name that starts with an integer, so that won't work in a structure either. This last one has a piece of something that we would call recursively declared. It has something of type struct f, but we haven't finished declaring struct f, so the compiler won't be able to figure out how much space it needs to set aside for something of struct f until struct f has been fully defined. So this is the only structure definition that is valid. All of the interior fields have valid syntax, and there's no recursive definitions. So structure B is the one that is valid. Once we have our definition, we can start to make variables of that type. We could treat struct case the same as any other data type that we've been using before. We can make a single instance of type struct case. We can also create pointers of this type. And we can make arrays in both 1 and 2 dimensions. So we could have 10 cases of soda, or we could have a display of sodas, like at the store, where there might be 5 rows and each row has, say, 8 pieces in it. So now that we have these, we need to keep in mind how we're going to access the interior fields for this variable. We'll talk first about standard usage, and when we say that, we typically don't mean pointers. So when we have a variable of type struct case, and it's not a pointer, we can use a period or the dot operator to access the interior fields, like num bottles, which is an integer. So we can make this a case of 12. But the other one, the other interior component to struct case, the other field, is a string. So we need to use string copy to give a value to soda type. And we'll say we're storing Pepsi. And so this would initialize something of type mySoda. There's 12 bottles of Pepsi here. When we expand to arrays, we now need to first go to the correct location of the array. then we can access the interior field of that element. So we would first index the array of sodas and then use the dot operator to access num bottles and soda type. So this would initialize the ith case of soda. We go to sodas at the ith index and access the interior fields to get num bottles, which is an integer, or soda type, which is a string, so we can copy Pepsi into the ith soda type for the array. And it's very similar when we get to two-dimensional arrays, except we now have to specify two different locations. So we can go to the display at the ith row and the jth column and access the structure there. But it doesn't change the underlying nature of the field. Soda type remains a string, so if we want to modify it, we still need to use the string functions. We just need to go to the ith row and the jth column of display to access soda type in order to copy Pepsi into that location. So now let's look at a couple of example functions. This is very similar. Instead of soda type, it says name, but otherwise this is our same structure. Struct case says consider the following structured definition for a case of drinks. Write a function that will print the contents of a single variable of type struct case. So we just want to print one case. And since this is a print function, it can be a void function. We want to print one case. And it should take in something of type struct case, which we can call whatever we would like, and print out the contents. So we're going to take in something of type struct case, print it out, and then return. We're not returning any values. This can be a void function. This only operates on a single instance of case. So we'll print out the contents of the case, including the type of drink that is stored in there and the number of bottles that we have. So we'll print out there are X bottles of blank in this case. And we're going to get those values from the structure. So we're going to access my case with the dot operator to print out the number of bottles. And the other field is a string. So we're using %s for that. We'll print out the name that is stored in there. And that is all that is needed to print the contents of one case, so then we can go ahead and return. And we expand on this a little bit in the second example. It says, consider the same structure definition. Write a function that will print the contents of an array of type struct case. So this just prints one. Now we want to print several. This is still a print function, so we can still make it with a void return type. We're going to print cases. And we're expecting an array of type struct cases. We'll also need the length of the array, so we know how many cases there are. So you could go with length or num cases. Both kind of represent the same thing. We'll need a counter to traverse our array of sodas. To start at 0, we go to num cases. We could, for clarity, add in a little bit of a header since we know there's probably more than one here. Then there's going to be a number of bottles and a type of drink for each of these. So we can make a little header for that. And then inside our loop, we'll print out those matching pieces of information, the number of bottles and the name of those that are in there using the %s code, where the integer is coming from the array in the ith location and the interior field num bottles, and the type of drink is coming from the ith location of the array from the string field, which is called name. And we'll want probably a new line character to really set up our nice little table that starts with bottles at the top and the type next to it. We'll print out the integers, and we're separating both of these with a tab, so it should look really neat as it's printing out all of our numbers in one column and all of our types in the column next to it. So now we can go back to pointers and structures, which are a little bit unique. There's an alternate syntax that you can use when it comes here. There's two different versions. You can first, what we would call dereference, go to where my soda is pointing, and then use the same dot operator that we've been using for everything else to access num bottles or soda type or name. But we can also use this arrow notation, which accomplishes the same task. The arrow notation is actually the more common notation, so you'll see that more often from experienced C programmers. And this will take us to our last example question. Consider the following structure definition for a case of drinks, same structure we've been working with. Write a function that will initialize a variable of type struct case using the following prototype. So we're restricted in our prototype this time, it's been provided. And what this is providing to us is the case that we're trying to initialize, the initial number of bottles, and the initial type or name for the drink that we're going to put in there. So we're given all of the initial parameters and a pointer to the structure that we're trying to initialize. So this function is initialize case, where initialize is abbreviated to init. So what we're going to do is we're going to copy the parameter bottles into num bottles, and we're going to copy the parameter soda into the field name for new case. So we just have to be careful of our syntax here. We need to access new case, which is a pointer. We need to access its num bottles field and put the number of bottles there. And we need to do the same thing for name, but name is a string. So we're going to use string copy and copy into new case the field name this soda string that we've been given as our parameter. And once we've initialized both pieces, we can return, because that is the entire purpose of this particular function. And that is all the examples that I have for you for exam 3, all the material that we're going to go up to in the course, and chapter 17 is not included. So I hope that you're feeling well prepared, and if not, please do let me know. Good luck!